Okay, chapter 9, and I don't have very much paper. Aha, there's paper in here though. Is working with radicals. And radicals are things that look like so. That is your radical symbol. And in your radical symbol, you have different things that happen with that. Up here, there's an index. And the index is outside. If you have a square, there is no index, so you won't have an index there, but it'll be a square root, is what we would say with that. Underneath the square root symbol, or the symbol for a radical, is a radicand. And the radicand is, of course, the number that you happen to have in that position and what happens to hold that spot. So this is the piece that we're going to do a lot of work with. Also, we're going to look at whatever that index happens to be out there and come up with some different values and different things that end up happening with that. So we can come up with our values. Now, in some cases, these come out to be exact. In other cases, they do not. And it will indicate in your Hawks work of where to round to if you have to round them off. So in 9.1, we are going to take a look at square roots and cube roots. Suppose square roots. Square roots are, again, we've got our radical symbol, no index out here, and the radicand they might put underneath there might be 49. So if they put 49 under there, what we are looking for is two values that are identical to each other that give me 49, but my single answer is only going to be one of those. So the square root of 49 would be 7. So then if you work it backwards and take 7 and square it, you get 49. And if you take the square root of 49, you will get the base of your square, which happens to be 7. And so that's kind of the direction that we're working with those, is we're going from one spot backwards into the other spot and coming up with our values that we happen to have. So what about the square root of 64? What will it be? 8. All of these, you should probably know the random square roots. They tell you to know your square roots up to, I don't know, I think it's like 39, or not 39, but up to 12. So if you get by with the square root of 144 and you know it, you can come up with your values that you happen to have in there. So we got our square roots and we got our information with those. And what happens? The square root of 0, what does it have for a value? What's the square root of 0? Square root of 0 is good old 0, because 0 squared does end up equaling 0. Now, realize that with these things that you have to be careful, because actually, if I had the square root of 49, the square root of 49 could be a positive 7, or it could be a negative 7, because if I take a negative 7 and square it, I also get 49. In most cases in Hawks, it's going to tell you that you will not worry about this part unless you have the negative square root of 49, and with the negative sign out in front, what does that tell you? It's going to be negative, yep. This tells me that this whole thing, when I get done with it, my answer is going to be a negative 7, not a positive 7, because this negative symbol out in front tells me that. And so I end up with a negative 7 for my answer. But if the negative is underneath the radical, what happens then? Well, if it's underneath the radical, is there a way to get a negative 49 and have two identical numbers to get it? When you look at that one, you might say, well, I could multiply negative 7 times negative 7, but when I do that, to be identical, they have to match each other. And so negative 7 times negative 7 is a positive 49, okay? And you can't just say a negative 7 times 7, because then these two do not match each other. They're not the same. So therefore, what you have on this one is you have basically no solution, or it's considered to be a non-real number. So in Hawks, it's going to give you whether it's you can come up with an answer, such as 7 if it's straightforward to square root of 49, or you can come up with the answer of a non-real number. It will? Okay, that's good. So on your calculator, you're going to find that out. Because, again, if you stick the negative in with that 49 underneath your radical sign, you're going to come up with that. Now, where is that radical sign on your calculator? Well, if you look at your, you have an x squared key on your calculator. The key that's right above it, that's on the base of your calculator, is where your square root happens to be. And so you'd have to use your second key to get to that. So be aware of that one. So this is considered non-real. This 7 up here, or this negative 7, those are considered to be rational. Now, what's rational? Rational means that it's a solid number, or it has a terminating decimal or a repeating decimal. So should I write that out? Probably better. Rational numbers are a whole number, a repeating decimal, or a terminating decimal. And you don't find very many that are going to be repeating and terminating when you get into some of these. You're going to notice that a lot of them are going to be straight whole numbers. Because when you start looking at square roots that are not perfect squares, such as if I gave you the square root of 2, and that one I can't just come up with what the value will be, can I? Square root of 2? Can I just come up with what it's going to be? No, unfortunately I can't, but I can put it on my calculator. So if I put it on my calculator, I would go second, hit my square root key. It's going to give you a parenthesis on your calculator. You're going to put in the 2, close it with a parenthesis. So get in that habit of closing these, because as we move on with other stuff later on, you're going to need to make sure that you get that closed in there, because if you close it, then you'll know that you're going to get your correct answer out of it. And then hit enter to get your equals. And it'll tell you round to 3 decimal places. So if I round it to 3 decimal places, what happens? What does it come out to be? 1 point, what was it? 414. Okay. If you look at this on your calculator, notice there's no pattern to it. Notice how it just keeps going. There's no combinations of anything. It kind of makes you think it might get a pattern in here, but it has no pattern, and so that's why we round it off. And this would be considered irrational. And irrational is a decimal that does not repeat or terminate. Okay, so that's our 3 definitions. We've got our rationals, which those are whole numbers or the repeating decimal or terminating one. Non-reals, which we can't work with just yet, but we will later on when we get into imaginary numbers, which is later on in the chapter. And then we have the irrationals. And irrationals, again, are those ones that don't terminate and they keep going and not repeating in any format or any way that you're looking at. Okay? What was that? What's terminate? Terminate means that if you had a half and you turn the half into a decimal, it terminates because it comes out to be 0.5. Okay? Or if you had 3/4, 3/4 terminates too because it becomes 0.75. So that's what I mean terminates. It means it ends on your calculator when you divide it out. And so you come up with an exact answer, as opposed to having to round it off. Okay? And then I think you know what repeating means, of course, is a pattern that goes over and over and over. Okay? Good question to ask, though, that of what does end up taking place with those and coming up with your solutions. So then it just gives you a whole bunch of different examples in there. So what if I had the square root of 9? What would I get? Square root of 9 is 3. So 9.1 is pretty much straightforward. Then they may give you a fraction that you need to work with. So if we look at our fraction that we happen to have in there and see what it comes up to be, when I work with that one, I can break this apart, and we'll talk about that more in section 9.2, and put the square root of 25 over the square root of 36. So my answer comes up to be the square root of 25 is 5, square root of 36 is 6, and so that becomes my answer. Okay? So what about this one? The square root of 134. A negative square root of 134. What would my answer be? So 34 is not a perfect square, so we need our calculator to help us out with that one. And so let's see what we end up with for that one. Do you have an answer?
Would it be negative?
Yeah, it would be negative because the negative is sitting out in front.
Negative 11.576.
Okay. Now, if we have that on our calculator, and Hawks has a habit of putting next to some of these, once we get our answer worked out, they may put that it's rational, irrational, or non-real. Which one would you put a check mark next to? So if we go back to our calculator and take a look at it, does it terminate? Does it repeat? Doesn't repeat either. So we would put an X or fill in the circle in front of an irrational, because again, it's not a solid decimal that terminates or repeats in there, and so it's irrational. How about the square root of a negative 81? What happens with that one? Pardon? Can't do that, right? It's a non-real. Okay? Non-real. Because if I go to put this on my calculator, remember that's kind of like that negative 49 we had earlier. I can't end up doing anything with that one, and so therefore that is what it ends up becoming, is a non-real that we're working with. How about this one? The square root of a 0.0016. What's that one? So what would my answer be? First off,
0.04.
okay. Now, is it rational, irrational, or non-real? It would be rational. Okay. All right. Got the idea between those and coming up with what values they happen to have? And again, it's just going to ask you that stuff to see what you come up with. How about the square root of 113? Okay. And what was that?
Irrational.
Irrational, because again it has no pattern on your calculator and so forth. Okay. Think you got these? Okay. So 9.1 doesn't have a whole lot of stuff in it. It's just basically pulling these things up and getting you used to doing perfect squares and things in there and so forth. So there are, again, I thought there were cubes in there, but I guess I don't have any cubes in that part, and coming up with what they end up simplifying out to be. But anyway, if you did have a cube root will have a 3 up at the top of it. And it has this 3 in here, which signifies that I want 3 identical numbers that give me my answer that's underneath. So if I put 27 here, so my radicand is 27, my index is 3. So what I'm going to look for is 3 identical numbers that multiply together to give me my number underneath. Okay? Now, in this case, when you've got a 27 there, what number would give me 27 that I multiply it by itself 3 times? 3. 3 times 3 is 9, times 3 is 27, so my answer is simply 3. Now, where do I find the cube on my calculator?
Math.
You go to math, and down to number 4. Down to number 4. And when you click on number 4, it will put it in your screen like so with a parenthesis. And you need to put whatever your number is, in this case 27, close it with a parenthesis, hit enter, and it will give you the answer of 3. Okay? Now the thing about cubes that you can do with those is we can do negative numbers with a cube. We cannot do negative numbers with a square root, a 4th root, or a 6th root, but we can with a odd root. We can come up with our answer for that one. Because if you stick this on your calculator, it's going to give you the answer of negative 3. Okay? So if we have cube roots, we have no non-real numbers. The only place we have non-real numbers that shows up is if your index is even. So I'll put that up here and write that out for you as well. So if the index is even, 2, 4, 6, 8 continues on, all negative radicands can not be solved and are non-real. But we know every positive one can be solved, so that's the only difference in there. So if the index is odd, such as a 3, a 5, a 7, etc., the negative radicand can be solved. Okay, so we can solve that one and come up with what our answer is. Because a negative times a negative times a negative, so if you had an odd number of negatives, going back to those rules we learned way back when, if you have an odd number of negatives in there, then what you have with that is that you end up getting your answer to come out with that. And so we have answers that we can come up with if the index is odd. All right, make sense? Oh, over this way? Yeah, I cut off my first words, didn't I? Okay. Yep. So you can come up with your values that you happen to have in there for those and getting your answers to work out. So 9.2. 9.2 is simplifying. Yep.
Here's a problem on 9.1 that I don't know if you went over, but it has 7 plus 3 and then a radical sign with 5 under it.
7 plus 3? And then it's got a what under it?
5. It has a radical and then a 5 under it.
This has a radical over it.
No, and then it's radical and then 5.
Like that?
No.
Oh.
No,
I have to come look.
7 plus 3 and then radical.
That's a 9-1? Oh, okay. All right. What we needed was this. And before I get into 9.2, let's put that one in there. 3 plus 7, the square root of 5, right? And they want the answer to this. So I guess I left those off. I don't know why I didn't have any in my samples in here. I guess I was thinking they were in the next section for some reason. But we'll take a look at it. So how do I solve this? So on my calculator, all I simply put on it is 3 plus 7. What's happening to 7 in the square root of 5?
You got the 7 and 3 mixed around. I don't know if that would.
Oh, well, it's not going to make a difference on this one. Okay. What's happening between 7 and the square root of 5? What's going on? These two are next to each other, so it needs to do what? Multiply. So I'm going to put multiplication on my calculator. Do my second, my square root. Type in a 5, close it with parentheses, hit enter, and I will have my answer. And again, it tells you to round to a certain spot. So round it to what location? Or should we round it to 3 places?
3, so it would be 18.65.
Okay, and that would be my answer that I type in.
No,
right?
the actual answer is 13.6.
But remember, I got my 3 and my 7 backwards.
Oh, that one.
Okay? So if I put my 3 and my 7 the way you had it, 7 plus 3, the square root of 5. So let's try that one. So if I try this one, I'm going to have 7 plus 3 times the square root of 5 equals, and what does that come out to be? So that should be your 13 point, what was it?
13.738.
7, what was the rest of it?
083.
Okay. So 13.708 should be your answer. Comes up with that one. All right. It's just a matter of having them backwards. So basically what this was an order of operations problem. And the order of operations problem just involved a radical as opposed to some of them we had in the past that didn't have radicals in them. So that's the only basic change with that one. So I think you're okay with that now? What do you think? Ready to do another one? Brooke, you want another one?
Sure.
Sure? Okay. Another one. Maybe we have something like 3, the square root of 2, plus 4, the square root of 7. What's that one going to equal? What comes out of that thing?
I got
14.826. Is that what you have too? All right. Hey, if that's what we've got, could be. Never know. No, I think you're okay. I think you probably got it right. Okay, does that help now? Hopefully. Okay. So those are just kind of an order of operation thing that was thrown in there. So 9.2 is simplifying radicals. Now, in 9.2 or 9.1, we just basically took all these radicals and we just solved them based on getting a solid decimal answer or a rational answer or an irrational answer out of those. In 9.2, this is probably one of the trickier pieces in the whole chapter. But what they do in this is there's 2 separate properties that are involved. So, properties of square roots. And in the properties of square roots, what we have is the first property is the square root of a times b is equal to the square root of a times the square root of b. What this means is if I take my radicand and I break my radicand into 2 separate things that multiply to give it to me, I can break those apart and see if one of these happens to be a perfect square. And so as we work with these, we're going to see what we happen to have in there. So an example might be the square root of 27. If I look at the square root of 27, it's not a perfect square. If I put it on my calculator, it doesn't come out perfect, but it comes out as a decimal. But if I want it as perfect as I can get it, because when you round and put a decimal in your calculator and we've rounded it off, we've manipulated that number and it's not exact anymore. But if I want an exact one, I can take this 27 and break it down to 9 times 3, correct? Is 9 times 3 27? Yeah. And what do I notice? Well, I notice 9 is a perfect square. So if I take the square root of 9 times the square root of 3, my answer for this is going to become the square root of 9 is 3. Can't take the square root of 3. And so my answer comes out being a combination of a whole number value and a radical value. And so that's what I'd end up doing with these, is I'm going to start breaking them apart so that they don't come out to be decimal representations, but they come out to be values that I can look at and I can work with as those. The second rule, and there's only 2, says that if I have a over b, what was that? Over, okay. What this means, if I have the square root of a over the square root of b, I can end up solving that in that format. Then in the top, if I need to break that apart like I did up here, I can. If I need to break the bottom apart like I did here, I also can do that. And so I can start to see some stuff that might cancel out, and I might be able to work with in a little bit different manner with those. And so that's my two rules. Okay? So basically it's just saying I can break stuff apart in there and come up with what my values happen to be and what happens to work out with those. Okay? What do you think? So far so good? Okay. So now what we want to do is we want to work with some of these. So if I had the square root of 450, and there's three possibilities, and they go through all of the different possible approaches in your sections. So approach one. And you can pick out whichever approach you want to do, and we'll go and use this exact same one for all of our approaches and see what one you happen to like the best. So if you know what your perfect square roots happen to be, we could look at 450 and we could say what it's made up of. Well, and you would look at it and say, okay, does my our perfect squares go into this, and which ones do? Well, 4 doesn't go into it, does it? Does 4 go in there? 4 is a perfect square because 4 is made up of 2 times 2. Does 9 go into it? Will 9 go into 450? What does it go in there? Okay, so I could say I have the square root of 9 times the square root of 50. Okay, so we've kind of broke it apart a little bit there. We've got one perfect square. But then what I'd have to do is go back and look at 50. Does 50 have any perfect squares in it? Yes or no?
25.
Yeah? Okay. So I could have the square root of 9, square root of 25, and the square root of 2 as my pieces that all multiply to give me 450. We all agree? Yes or no? Okay. So what's the square root of 9 is 3. The square root of 25 is 5. Square root of 2, not perfect, so I can't take that one and do anything with it. So my answer comes out to be 3 times 5 is 15, the square root of 2. So basically all I did was to look at this and say, okay, what went into it? Okay. So I noticed that the first 9 went into it, then I had 50, and automatically popped out 25 out of that one. And so we knew what we were doing with it. So my answer came out to be 15, the square root of 2. Okay? Yes or no? So far so good? Okay, that's approach 1. Now again, you're going to be able to pick whichever one you want to use with these. Approach 2. And in approach 2, what do we have going on? Well, in approach 2, you still have the square root of 450. But in approach 2, instead of breaking it into all of our radical separate pieces, they just take it and find all of the separate ones, but leave it underneath a radical sign altogether, and then take the square root of 9 out, take the square root of 25 out, and leave the square root of 2 underneath, and get 15, the square root of 2. Okay? Not much different than approach number 1. The one that I like the best is approach number 3. Because in approach number 3, you start to see all of your pieces that happen to be in there, and I don't know if you guys have been real into doing prime factorizations. But within these, if I take 450 and I break it to its prime factorization, 450 is made up of 45 and 10. 45 is made up of 9 and 5. And 9 is made up of 3 times 3. 10 is made up of 2 times 5. What I have when I break that apart is under my radical, I have 2 times 3 times 3 times 5 times 5, and I don't have to think about what are perfect squares in here at all. I don't have to think about that at all. And so my values that I happen to have in here, then the only thing I need to go through and look for, because my index is 2, all I need to go through is look for combinations of 2's, and that's when I pull out 3 times 5, and I leave anything that's not in doubles, and I have my answer of 15, the square root of 2. I don't have to think about what's perfect squares. I don't have to think about what can I take out of it or pull out of it. All I need to do is make sure that I can break it down and get it to its prime factors, and then I can pull out what I need. Okay? That makes sense? Hopefully. Okay? The other two, I have to think a lot in here. I have to think about, okay, what's going to make my perfect squares or roots values in here? And so down here I don't have to think about that. All I need to do is do this, write them all out, put my groups of 2 together, and pull that number out as I see it in there. Okay? So I think it's a little easier to do that one than to do the others. I don't know. What do you guys think? Yes? No? Might be? Okay. And again, this is probably in this chapter, and we use this all the time throughout the rest of the chapter. That's kind of the more complicated part that we happen to have in there. And so you can end up simplifying those. And when your index changes out front, what do you got to do then? Well, all you got to do when your index changes is just change the pattern and the groupings of numbers that you circle. All right? So instead of, if this were a 3, I would then find groups of 3 things inside of this prime factorization, circle those, and pull them out. Okay? And then you would have them out of there. And you'd know what you're taking out, then multiplying in the end. Sam, you got a question?
Yeah. How come you didn't? Okay, I get it. Okay.
What were you going to ask?
I was going to ask how come you didn't take the 45 and 10, but then I got it because they have little tree branches off.
Yeah, because 45 branches down to 9 times 5.
Yeah.
And 10 branches to 2 times 5. You want to get these broken down all the way. Even though you ran across, notice 9 was perfect square root, you get a perfect square of 9. Because I broke it down to 3's, I then knew what I was pulling out here. Okay? Yeah. And so that's kind of the key to that part, is that I know the pieces that I happen to be pulling out. Okay? All right, let's do some more of those guys and get some more practicing done with that. So, how about the square root of 300? What would it be if I broke it all apart and pulled out different things? So if I take 300, break it to its prime factorization of 30 and 10, 30 breaks down to 6 times 5, 6 breaks down to 2 times 3, 10 breaks down to 2 times 5. We okay with that part? Again, all of these numbers at the tail ends are your prime numbers. And again, the review of prime numbers are 2, 3, 5, 7, 11, 13, 17, and going on and on. So these are your prime numbers. So under my radical, what do I have? Well, I have 2 times 2. I have 3 times 5 times 5. Now I've got them all. Okay? And so what can I pull out? Again, circle in groups of 2's. So I can pull out a 2, I can pull out a 5, leaves a 3, and so what's my answer? 10 to the square root of 3. Alright? So 10 to the square root of 3 is what I end up with for that one. Okay? Yes or no? Okay. How about square root of 28? Now this one, again, with your toolbox, now you've got all 3 different pieces to it. You might look at 28 and know that 28 is 4 times 7. And so then you would know that you can pull out a 2 and leave a 7. Okay? Are we all right or not all right? Okay. How about this one? Square root of 27 over 16. And this also works if you don't know what a perfect square happens to be, because if you break them all down, you're still going to get to that same results with those. Our rule says I can break it apart. And so what am I left with? 7 is 9 times 3, 3 times 3, so 27 is 3 times 3 times 3. 16 we know is 4, and that from before. So I can pull out a 3, leave the square root of 3 all over 4. Now that's exact, okay, because I have not turned that square root of 3 into a decimal at all. So I've left it exact in there. All right, what do you think? Pretty good so far? Okay. Now, if you have numbers such as, if we had the square root of 288 over 36, and if you notice 288 over 36, what can we do with that? Can we reduce it at all? Does it reduce? You can always look inside of here and see if it reduces. And notice they're both even on the end, so that would tell me that 2 would go into them. But sometimes it might mess me up, because 36 is a perfect square on the bottom too. So I don't know. They say that you should reduce them if you can. And in this case, well, if I reduce it by 2, what happens? I get 2 goes into there 144 times. 2 goes into 36 18 times. Does 144 and 18 reduce? Yeah. 2 goes into 18, 9. 2 goes into there 72 times. And then what do I notice? 72 and 9 reduce, because I get the square root of 8, because these two reduce completely. A 9 goes into itself once, goes into 72, 8. So now all I got to do is get the square root of 8. And what's the square root of 8? In perfect squares. It's going to be 4 times 2, or 2 the square root of 2. So most of them in Hawks will reduce. Now if you didn't reduce it right here, let's say you worked it out and you worked through the whole thing, you would end up taking the square root of 288 over the square root of 36. Square root of 36 is 6. 288 is 2 goes into there 144. That gives me a 12 and a 12. I may not want to go any farther than that, because I've got 2 that I can pull out right there. So if I take 2 times 12 times 12, gives me 12, the square root of 2 over 6. I still get the exact same results, because 6 and 12 cancel. So I'm left with 2 to the square root of 2 for my answer. So it still worked. So even if you didn't cancel it, you could still work the whole thing through and not cancel your stuff out as you go. Okay? So depending on what you want to do, I would look at them always and see if there's something I can do to reduce that stuff. And in most cases, what I found when I did the Hawk stuff is this denominator disappears altogether. I don't think there's very many that it doesn't. And you would know as soon as you take 288 and divide it by 36, if you came out with a decimal, you know they don't divide evenly. But I think in most cases, what Hawks is set up do end up reducing and coming out of there evenly when you work with those. Okay, and the other thing they stick underneath your radicals is letters. And if you have variables, what you're going to look at is your index. So in this case, my index is 2, and you're going to take the exponent and divide it by the index. This is the exponent on the variable removed from under the radical. The remainder is the exponent left under the radical. So, if I have the square root of x squared, the exponent is 2, the index is 2, so 2 divided by 2 is 1, no remainders, so my answer is just simply x to the first power because that was my number out here. Hopefully that makes sense. Still writing, okay. Yeah, it takes a bit. Like if I had the square root of x to the 5th, what would end up happening? Well, I would again take 5, divide it by 2. 2 goes into 5 twice. But I have a remainder of 1, so that means I pull out an x squared, because that's my whole value, leaving me an x to the first power underneath my radical, or just plain x would be still remaining underneath there. Okay? So x would still remain under that one. Now the other thing you need to be aware of is that in Hawks, they will say that x needs to be, this x that we pulled out of here, needs to be inside of absolute values because what can we never have under our radical? If it's a even index, we can never have a negative number. So x has to be positive. So whatever value you would put in for x would have to be a positive value that we're working with, because I can't take and I can't use anything that's not. Now, do they get picky and make sure you put all these inside of those? No. After they tell you that, then it's kind of like you're left to just put the x out there. You don't have to put it inside of absolute values on your answer. So they will signify and know that you know that that has to be a positive number that we're working with and putting that in there for those. So that's the part that has to play a role in that piece. Okay, so then if they give you more than one letter under here, and let's say we have an index of 3, and I have x to the 7th, y to the 6th, what do I pull out and what do I leave? Is there anything left under there? Well, you do the same thing here, and you get so you can do it in your head, because you know 3 goes into 7 twice, so I have an x squared out front. And as you work with these, leave your radical off to the end so you can stick anything under it that you have left over. 3 goes into 7 twice with a remainder of 1, so I know I have an x left under my radical. Okay, 3 goes into 6 twice, so I have a y squared out in front, but I have no y's left underneath because I've removed it. You okay with that part? Yeah? Okay. Pretty self-explanatory, pretty straightforward stuff that you're dealing with when you deal with exponents in there. And again, your index can be any value that they want to put out there. And so just take this, divide it into this number, leave your remainder underneath, pull out what you can. Okay? For those. And they do go and they put square root of 36y to the 5th. Might be an example they give you. So numerically, we work with the number part first. So what's the square root of 36? It is 6. And then I have y to the 5th, so that means the index is 2. So 2 goes into 5 twice. So that gives me my y squared, but still left under my radical is going to be a y. Okay? And so this is my full-fledged answer that I have for that. So you kind of got to pull some things out and maneuver some stuff around and get your pieces to come together with those. Okay, how about this one? Square root of 12, x to the 7th, y to the 8th. What would I get? So what can I do? Well, I got 12, so what can pull out of 12? So if you take 12 over here, 12 is made up of 2 times 6, and 6 is made up of 2 times 3. So that means I have a 2 times 2 times 3. So what can I pull out? Well, I got a group of 2's, so I can pull out a 2, correct? Okay with that part? And under my radical leaves a 3, because that 3 can't come out. 2 into 7 goes 3, leaving me an x under the radical. 2 goes into 8, 4. So y to the 4th comes out front. Do I have any y's left? Nope, no y's left, and so therefore that's my answer. Okay? What do you think? Yes or no? Numerically, make sure you break them apart, unless you can know that they're perfect squares. Then you wouldn't have to break it apart, but break them apart so you know what you got in there. Okay? With those. Okay? How about this one? Negative square root of 48. So if you take 48 and break it all apart, it's prime factorization stuff down the side. Then we've got 1, 2, 3, 4 2's. And so I got 2 times 2 times 2 times 2 times 3. And then I can pull out a 2. I can pull out another 2, leaving a 3. and I get 2 times 2 is 4. And it's negative because I got a negative out in front, so it's negative 4 to the square root of 3. Now you could also, now that we know about what exponents are on our bases, I could count these up, 1, 2, 3, 4 2's, and do the exact same thing I did with my x's before. But when I'm all done, 2 goes into 4 twice, so I have 2 squared outside, no 2's left. I would have to go back and multiply that out though. Make sure that you remember that. This would have to be multiplied out to be 2 times 2 or 4. So you have to come back and give yourself that answer that you have. But you can go through and do your exponents the same way. That would show you what you have left underneath. Okay? So you can take them and circle them, like I did up there, or write them as the total number that you have and do your index out in front and see what comes out of that. How about this one? Square root of 109 x to the 7th all over 121y squared. What will happen to that one? Can we break 109 apart? You couldn't, and you can't. Because if you check 109 for all the different primes, 2 doesn't go into it because it's not even. 3 will not go into it because 1 plus 0 plus 9 is 10, and 3 doesn't divide into 10. That's the sum of the digits rule. And 5, because it's not 5 or 0 on the ends. 7 doesn't go into it because 7 goes into 10 once, leaving me a 3 and a 39, and 7 doesn't go into 39. And then 11 is the next one, and that's even bigger than what you have up there. So 109 does not break apart. So 109 needs to stay underneath the radical. But what about x to the 7th? Can I do anything with it? X to the 3rd out front and an x with the 109. And then if I move to my bottom, 121 is a perfect square, so that's 11. Y squared is a perfect square because 2 goes into 2 once, pulls out a y, and that is all I can possibly do to that problem. Now in Hawks, if you've noticed, when you try putting in these exponent pieces, sometimes it's hard to get the second piece in there. You ever tried that? You run across Hawks and you try to stick your stuff in and you go X, and then you do on your keypad, you put your power in there and you stick your power in, and then you have problems and sometimes getting your stuff in there. So just be careful with that sometimes you get locked into doing some different things in there with that. So if you have that problem, then you can just pull that 3. Don't put it in first, type your rest of it in, then go back and put in your 3. Yes? The y's cancel out.
Like 11y, like you're trying to get the 2, like 2 times. I'm not.
Okay, are you thinking? You're not thinking this way.
Like, oh no, because you said like the index would be 2, right?
Yes.
So,
Mhm.
like, so 2 times 3, I understand when 3 is out there, but I didn't know if the y was up because it's...
No, because what you're doing is you're taking this index of 2, you're dividing it into this 2, and it goes in there once, which means I have to have y to whatever that value is, so y is going to have the exponent of 1. Okay? They can't cancel out because there isn't anything to cancel them with. In order to cancel it, you'd had to have a y up here to cancel this way. But you don't have a y, you have an x, so you can't cancel. It's still there. Okay?
Will they ever have a y?
Can, sometimes. Yeah, sometimes. Sometimes they might have that where you got your double connection there and what you have happening with that. Okay? How about this one? Cube root of a negative 192.
You can't do it, it's even.
What was that?
You can't do it, it's even.
Oh, no, because the index is odd, I can do it. You know, just be careful because this has got to be an odd index in order to do that. So then you're going to take your 192 and break it apart. 2 will go into it because it's even. 2 goes into 19 9 times. 2 goes into 12 6. 2 will go into 96 48 times. 2 goes into 48 24 times. 2 goes into 24 12. 12 is made up of 4 times 3, and 4 is made up of 2 times 2. Okay? So if we break it to its prime factorizations, then we can see what we've got in there. So if I count up all my 2's, 1, 2, 3, 4, 5, 6 2's, 2 to the 6th. And what else do I have left? I've got a 3. So then what can I take out of there? So now I'm back to the exponent, so 3 goes into 6 twice. So I can take out a 2 squared, leaving me with the cube root of 3, because I can't take that out at all. And so 2 times 2 is 4, cube root of 3. So then I can know what I've got to pull out of there and what stuff will work with that. Okay? Yes? Again, I didn't have to know any of my cubes at all to do this. All I needed to know is to do this prime factorization thing. Yes, it would all be negative. Thank you for reminding me of that. So that whole thing would come out to be negative when I pull it out of there. Yeah, because I need to put negative in front of that. Yes. Okay. Okay. What do you think? Okay with those or not? Or we need to do a few more? A few more? Okay. So how about, let's see what you get for this one. Cube root of 216 y to the 6th. Straight on there. You can always try your numbers and see if they are perfect cubes. In this case it was, and I didn't realize it until I went through my numbers in there, but you can always check them to see if they are perfect cubes or perfect squares before you go to this method. But again, if they come out to be decimals, then you got to go back through and break them apart to see what you get. And so we took 216, broke it apart, just prime factors. And I had 1, 2, 3 2s and 1, 2, 3 3s. Wrote them up here. 3 went into 3 once, pulled out a 2. 3 went into 3 once, pulled out a 3. Then 3 went into 6 on my y, so I could pull out a y squared. And so my answer came up to be 6y squared. Okay? Again, it's just a matter of breaking these things all apart, coming up with what you would possibly have with them. How about this one? Square root of 96 x to the 4th over 100 y to the 14th. Bottom of this one's pretty easy. 100 is 10, square root of it. Square root of y to the 14th is y to the 7th, so the bottom gets done pretty quick. What about the top? That one's kind of got a lot of pieces into it, because not a lot cancels out of it as you go through and do it. So you can get rid of your 2 with your 10, those cancel. Of course, we got to go back here. 96 breaks down to 2 to the 5th times 3, x to the 4th. 2 goes into 5 twice, so x squared comes out, 2 squared comes out, leaving a 2. 3 I can't do anything with, and 2 goes into 4 twice, so I take out an x squared. So then 2 squared is 4. 4 and 10 will cancel. 2 goes into 4 twice. 2 goes into 10, 5. And so I'm left with 2 out front. X squared, square root of 2 times 3 is 6. And finally 5 over y to the 7th. And that would be my answer. Okay or not okay? Yes? Okay. So let's... 9.3 is, if I write a 9 and a 3, 9.3 is looking at turning radicals into fractional roots, or fractional exponents. So turn radicals into fractional exponents. And so basically, if you have nth root, meaning that our root can be any index value. So if n is up here, and a is underneath the radical, we can say that this is equal to a to the 1/nth power. So we get fractional values in there for our roots that happen with these. So what in the world does this look like? So if we have a square root, and in our square root we have b squared. So if I turn this around equals a, then b is equal to the square root of a. And if b is equal to the square root of a, then we could also say b is equal to a to the 1/2 power, because it's a square root. Hopefully that makes a little bit of sense. But basically what you're doing is taking your radicand, which is underneath your radical sign, taking whatever your index happens to be and putting that as a denominator. So your index is the denominator. Of your fractional exponent. So we've got that index as our denominator of whatever we have. So if we have a cube root, which is b to the 3rd power equals a, then b is equal to the cube root of a, or b is equal to a to the 1/3 power. And it stands to reason on your calculator, if you go and you put something in as a number here and take it to that whatever that fractional exponent value happens to be, it's going to reverse it and come back to whatever your value happens to be for your base that you had in there. So if it's a 4th root, what do you think is going to happen? B to the 4th power is equal to a, then b is equal to the 4th root of a, or b is equal to a to the 1/4 power. And if we keep going, we could go to 5th roots and 6th roots and 7th roots and 8th roots and whatever. Or when we finally get to the nth root, we have b to the nth power is equal to a. Then b is equal to the nth root of a, or b is equal to a to the 1/nth power. Okay? So it's just taking it and turning it to fractional values. So if we start sticking some numbers in here, and we say 2 to the 4th power is equal to 16, then 2 is equal to the 4th root of 16, or 2 is equal to 16 to the 1/4 power. So it's kind of getting into fractional values and fractional results that we happen to have within those. Okay? Yes or no? A couple more? Okay. So if we had 3 to the 5th power is equal to 243, then 3, which is my base, is equal to the 5th root of 243, or 3 is equal to 243 to the what fractional value?
1/5.
1/5. Yeah. To the 1/5 value. All right. Another one might be 8 squared is equal to 64. So therefore, 8 is equal to the square root of 64, or 8 is equal to 64 to the 1/2 power. So you're just kind of turning those around. Instead of having the radical, you're going to end up having it turned into what value it would happen to be. What would take place with that. Okay or not okay? Okay. if we take those and we reverse them, and they give you, which they do in Hawks, they give you 36 to the 1/2. Well, because it's to the 1/2, what does that mean? Well, it means I have the square root of, 36. So what's the square root of 36? 6. So your answer is 6. Can you stick these on your calculator? Yeah. Now when you put them on your calculator though, if you take 36, use your caret key, but when you use your caret key, make sure you put your 1 divided by 2 inside of parentheses, because if you do 36 caret 1 divided by 2, it's going to take 36 raised to the first power, divide it by 2, and give you the answer of 18, which is not what you want. Okay? So be really careful when you're putting a power in there that's a fractional power on your calculator, because you're going to end up getting your value that you happen to have in there of what comes out of that. Another one might be 27 to the 1/3 power. So reversing it, the index is the denominator, is 3. The radicand is 27. And so what's the cube root of 27? And we did that one earlier. So what's the cube root of 27? Is 3. Yep. And another one might be 0.0001 to the 1/4 power. So that means I need the 4th root of 0.001. And what would it end up being? So what's the 4th root? And that's the way you interchange and go between these things.
0.1.
Yep. Yep, 0.1. And then they might give you a negative 32 to the 1/5 power. So that means I have the 5th root of a negative 32. And can I do that one? 5th root of a negative 32? What would come out of that? Negative 2? And I can do it because my index is odd. My denominator is odd. Okay? Now, if they had given me a negative 32 to the 1/2 power, that means I have the square root of a negative 32, so what would I have to write? Can I do that one? That would be a non-real at this moment. Next week we'll find out that we can do imaginary numbers with it, but...
Is that with the I?
What was that?
With the I.
With the I. Yep. Yep. That's what we get into when we do imaginaries. We put an I in there and then we can do whatever we want with it. Okay? All right. You all right so far? More of these? You okay?
Go back to that negative 2.
Yes?
At the end of the answer. How did you get the negative 2?
Took the 5th root of a negative 32. If I take 32 and I break it apart, I get 2 times 16. I get 2 times 8. I get 2 times 4. I get 2 times 2. 1, 2, 3, 4, 5 2s. And they're all negatives. Because a negative times a negative times a negative times a negative times a negative, 5 of them is going to give me negative 32. So I have negative 2 to the 5th power with the 5th index up there. That's how I got my negative 2. Okay? If I put it on my calculator and I did the 5th root. Now, if I do it on my calculator, I'd have to go to math. And under math, number 5, I think it is. Is it 4? No, it's some, I thought 4 was cube. Is it 4 cube?
Oh yeah, it's cube.
Okay. Now you go to the fifth one down under math. So if you go to math and you go to the 5th one, it's the xth root of something. Okay? When you do these though, you need to put in your index first. So you put in a 5, go to math, number 5, then you can put in, and it'll give you a radical, you can put in a negative 32 inside of parentheses and hit enter, and you'll get your answer. Okay? So that's where it's at on your calculator, if you're going to find it in there. So that's the location of where you get the 5th roots, or any higher root than 3. you would use that key too. But remember, if your index is even, you cannot do negative numbers. If your index is odd, you can, and your answer will be negative when you're done. Then you can just ignore the negative sign, really, and just know that it's going to be negative when you're all done with it. And you get that answer. Okay. All right. All right with those in? What do you think? Okay? All right. Now, the other piece that they add to this is they will take a number and they will say a to the m over n power. What does this mean? Well, if you are going to write this back into a radical notation, your n is your index. The m that's on top says we take the whole thing and raise it to the mth power. So you've got exponent, you've got an index on the bottom, but on top you have an exponent that you raise everything to. Okay? So one like that one might look like 8 to the 2/3. This means I have the cube root of 8, but when I get all done with it, I want to square it. Cube root of the base, but I square that whole thing when I'm all done with it. So what's the cube root of 8? Cube root of 8 is 2. Then, to be completely done with it, I square it. So 2 squared is 4. So my answer is really 4 when I work that one out. How about this one? 81 raised to the 3/4. So when I reverse it, I want the 4th root of 81, but then I want to take that whole piece and I want to cube whatever that answer comes out to be. So what will it come out to be?
27.
27? Because the 4th root of 81 is 3, right? 3 cubed is 27. Yep. 8 to the m over n, and all you can do with this one is just simply write it back into its format and put an m out in front of it. You can't do anything else with it, and you just write it into that location or into that spot. Okay? When you have letters involved, x to the 3/4, that means I have the 4th root of x raised to the 3rd power. Or you can also write this one as the 4th root of x to the 3rd power underneath. So you can write it both ways. And Hawks, I think, is going to look for this one as opposed to that one. So basically all it does is says what you have underneath here has an exponent on it. Numerically, it's easier to do these without putting that in there because you got to solve all those. But for letters, it's easier to just put the exponent in underneath on the x. And so you have it in that location and in that spot for those. What if you had y to the 2/5? What would that equal? And there isn't any math you can do with these. You just kind of stick them together and put them under there and do what comes out of them. So, what's it going to look like? Well, it's going to be the 5th root of y squared. Yep, 5th root of y squared. They bounce back and forth and ask you to reverse them if you have a number out in front. 5x to the 2/3. So what that means is I have a 5 out in front. I have the 3rd root of x squared, and that's what it would look like if I rewrote it. The 5 doesn't have the exponent on it, and so therefore it sits out in front. It's not part of your answer with that one. Okay or not okay? Not hearing much out of you, so I'm hoping you're okay. Okay. with those. All right. Now, if you have, this is where your laws of exponents come into play. And if you remember, the laws of exponents said that if I had a to the nth power times a to the nth power, what did we do to those? And that's why you have extra credit sections 5.1 and 5.2 to do, because 5.1 and 5.2 go back through all of those rules. Okay? You might want to do those before you hop into all of 9.3, because these end up helping you with that. So if I had a to the nth times a to the nth, we just simply took m plus n and came up with our solution. Remember, we added exponents if they're multiplied. If they are divided, we took a and we said m minus n and came up with our solution. But sometimes in these we ended up with negatives. And what do we have to do with negative exponents when we get them? They move to the bottom, or if they're in the bottom, they move to the top. Okay, so you've got that law in there. You have this one, a to the mth raised to the nth, or a to the m times n. That's when we multiply, because this n said I want to see this thing 3 separate times out there for that, and so that's what happens with that one. So you do have those pieces in there for that, and so you've got your sections in there that apply to those. Let's see, I'm trying to remember if that's all of the ones they give you in there. Oh, a to the mth over a to the nth raised to the third power. This one, you distribute each piece times your values that are in there, and so I end up with a to the 3m over a to the 3n, and then you'd end up combining these together, because you'd end up distributing that 3 by everybody that's in there as far as exponents go with those. 0 power gives you 1, so if anything raised to 0 power is 1 when you're done with that one. Let me see, I think I've got all of them that are in there. Oh, a to the mth, b to the nth, raised to the third. That is again a distribution, so I have a to the 3m times b to the 3n. So you get a distribution that's going on there, and you distribute it over those. But the key thing in 9.3 is they're no longer solid numbers, they're going to be fractions. Okay? So if you deal with fractions, when you're simplifying, you have to make sure that you know how to add, subtract, multiply, and divide fractions. So if I had x to the 2/3 times x to the 1/6, I need to, denominators or bases are the same, so I need to do what to my exponents? Add them. So I have x, and then my common denominator between 3 and 6 is 6. 3 goes into 6 twice, 2 times 2 is 4. 6 goes into 6 once, 1 times 1 is 1. So my true answer on this is x to the 5/6. And you would leave it like that. Okay? X to the 5/6, and that's what you'd end up putting into your problem when you ended up doing it. If you had x to the 3/4 over x to the 1/3, then what would happen with this one is I would need to subtract my exponents. So once again, I'd need a common denominator between 4 and 3, which is 12. 4 goes into 12. 3. 3 times 3 is 9. But this time I want to subtract because it's a division. 3 goes into 12, 4. 4 times 1 is 4. So I end up with x to the 5/12. Okay? And you can leave it like that because Hawks lets you put it in as a fractional value in there. Another one might be 2a to the 1/4 raised to the 1/3. Because this 2 is in here, it also needs to get a 1/3. So 1/3 times 1 is 2 to the 1/3. 1/3 times 1/4 is a to the 1 times 1 is 1. 4 times 3 is 12, or a to the 1/12. And you would end up leaving it like that. Okay? Yes or no? We good so far? Okay. How about a negative 36 to the 1/2 power? Can I do that one? Yes or no? What do you think? Can I do that piece? Okay, so I would put on this one, it is non-real. Okay, non-real because of the fact that I cannot take the square root, because remember this was what that means, of a negative 36. So be careful with even fractions on your bottoms, and making sure that you got negatives in there. So it's non-real for that one. Let's see. Other ones we got in here. 49, x to the 6th, y to the negative 2nd, z to the negative 4th, all raised to the 1/2. So we got some work in there to do. So first off, I got some negative exponents. So can I leave them where they're at? Switch them. 49 stays, x to the 6th stays, y to the negative 2 goes to the bottom, but z to the negative 4th comes on top. Okay with that part? All we did was move them around. That's again a rule that is in 5.2, I think it's in that section. But I still got my half out here. So I still got to distribute everybody by a half. So 49 to the 1/2. X, 1/2 times 6 is 3. Z to the 4th is z squared. And y squared is just simply plain old y. Are we done? Now if you type this into Hawks, Hawks would tell you you're not finished yet because of this piece. That really is the square root of 49. So square root of 49 is 7. X cubed z3 all over y. So you'd have to reduce that part because it is a square root when you've got a half in there with that one. Then they can give you ones that look like this.
Wait, there's 2 left.
Oh, 2. Thank you. Thank you for fixing that. Times the square root of a. Now when you look at that one, you think, yeah, I can't do anything with that. That all is kind of 2 separate radicals, so I can't really do a whole lot with it. But if I turn it back into fractional form, a to the 1/4 times a to the 1/2, I can end up working with it. Because now I can come up with a common denominator. Common denominator is going to be 4. 4 goes into 4 once. 1 times 1 is 1. 2 goes into 4 twice. 2 times 1 is 2. So I'm left with a to the 3/4. So you can work with some of those, and then if you turn this back into radical notation, it's 4a cubed. And you have an answer to these 2 separate pieces that you happen to have been given with that. Another one might be the square root of x cubed times the 4th root of x all over the cube root of x squared. Looks kind of weird and strange, but we can get it back into fractions. I think a lot of it is recognizing when you have to turn to fractions and when you don't have to turn to fractions. But as this sits here, there's not a whole lot I can do with it. I could pull out an x out of here, but it's not going to help me that much. I can't do anything with this, and I cannot do anything with that. But when I turn it back into fractions, this is going to be 3 halves, because remember the x, or the index is your denominator, your exponent is your numerator, x to the 1/4 all over x to the 2/3. So now what would I have to do? Yep. So what's going to be my common denominator? 12? Okay. 2 to the 12, 6. 6 times 3 is 18. 4 to the 12, 3. 3 times 1 is 3. Then in the bottom, 3 goes to the 12, 4. 4 times 2 is 8. So 18 plus 3 is 21 twelfths all over 8 twelfths. So what would have to happen to those two now? Subtract. And 8 from 21 leaves me with 13 twelfths, or x, the 12th root of x, because 12 goes into 13 once, leaving me a whole x out in front, and leaves me with 1/12. And this 1/12 ends up being that radical piece that's in there. I think Hawks lets you get away with, maybe they don't, I think they'd tell you this isn't simplified as low as it can go, and so you'd have to go back and break it apart within that one.
I have a question.
Where'd the 13 go?
Yeah.
Okay, if you take this piece, I need some more room over here. If you take that piece and put it back into radical form, the 12 is my index, the 13 is my exponent. So 12 will go into 13 once, so I can pull out an x. Remember how we got that one and we left what was left over underneath? And so that's what happens to that one, is that you move those pieces around in there to get it to work. If you have numbers out in front with some of these, which they do that too, and they give you things like 3x to the 5th times 6x to the 2/3, then what we can end up doing with this one is take 2 times 6, or 3 times 6 is 18. Multiply, since we're multiplying, this needs to be turned into thirds, just 5. So it becomes 15 thirds, because this has a 3 as a denominator. Since it's multiplication, 15 thirds plus 2 thirds is 17, 18x and 17 over 3. So I get 18 third root of x to the 17th, which I can pull out, 18. 3 goes into 17 5 times. Leaves me x squared underneath, and so my answer comes out to be 18x to the 5th, the x to the 3rd root of x squared.
Where did 18 come from?
3 times 6.
Oh, okay.
The numbers that are out in front. Yep. 3 times 6. So they get a little bit tricky with what they end up doing. How about this one? Square root of 81 x squared. What's going to come out of that one? I kind of throw one back in there. So this one's back to the first stuff we did, so it's 9 and just plain 9x. Okay, so there's not a fractional piece involved with that one. How about that one? Still the properties, because x to the 4th and x, this is to the 1. What do I do if I'm dividing? So 4 minus 1 gives me x cubed. And so my answer on this one becomes x, the square root of x, because I could pull out an x out of that one. Again, it's a lot of trying to figure out what in the world are they asking to do. Another one is they put a radical inside of a radical. What in the world does that mean? Well, this means if I turn this into fractional value, it means I have the fifth root of y to the 1/4. And what does that mean if I turn it around? I have y to the 1/4 raised to the 1/5 when I take that radical and turn it back into fractional form. So really I have y to the 1/20th. Again, turn this into fractions, turn that into fractions, and then multiply my fractions based on my rule that says I can distribute an exponent on the outside by an exponent on the inside and get y to the 1/20th. Now in this section you may find that you want to go back and take a look at definitely do the practice. Don't hop in and do certify in this. You will kill yourself automatically because you got to practice it before you can jump in to do certify. Okay, so make sure you do that. You might want to take a look and go back into the instruct part because then it gives you some more definitions of some things in there. But I think pretty much we got the idea of what type of stuff we got to do with it. What do you think?
Is this the hardest stuff?
This one is. This one's because it's got all the fractions in it and all that kind of stuff. So, but once you get this down, I think it's only in here that they give you the fractional parts. Later on in the chapter, it doesn't deal so much with the fractional pieces. But we need this part to do some stuff in chapter 11. So we're kind of off a little bit there with our stuff, but we still do need it. Okay? All right. One I did miss on this is when you have a negative fraction on the outside. What does the negative fraction on the outside mean? Well, the negative here means we take the reciprocal of what we have inside of here. So that means I need to take 27 on top, negative 64 on the bottom, and then put the 1/3 and make it positive on the outside. So when I do that, I want the cube root of 27 over the cube root of a negative 64. And so then I can end up doing that and get 3 over a negative 4 or a negative 3/4 would be what I'd get for that one. Okay? Alrighty.